Hello and welcome everyone. So I'll be explaining recent CodeCraft-21, Codeforces 711, Division 2, Problem C, Planar Reflection. Now, this problem is a very good one if you want to understand recursions, because it's a recursive DP. How I did was, it is a recursive DP approach. Using that approach, I did the problems, and it's a very good problem to understand recursion as well. So let's jump into the statements. I'll explain you in brief what the statement actually tried to say here. You basically have to find the size of a multiset where each and every element would indicate new particles that are going to be produced. Now, how the new particles are going to be produced, that's a big question. So we're going to be diving into the solution. First, explaining this statement, how the new particles are being produced. Now, okay, so the main thing is that, okay, initially you will have one point. Let's say the point A. This is the point, assume, and you would have at this point A will have a specific amount of mass. I can denote it as a kilogram. Okay, and also you're going to be given an integer n, where n will be like different barriers, you could say different barriers, something like that. And let's say you're doing an experiment on that particles, and to commence that experiment, what you would do is you will run out one particle. Initially, you would have only one particle, so answer would always be at least one. That's for sure. And that particle, to commence that experiment, that particle is going to have to go through this bunch of barriers that it does need to cross, and there's going to be some operations that or situations, circumstances that's going to be happening during that travel from one barrier to another. And what actually is going to happen is, let's assume that this is kg or kilogram, and this particle initially I will push him with some velocity to move forward, and once this particle gets past the first barrier, another particle is being produced, and it goes to the opposite direction, just like that. But when it goes to the opposite direction, the mass also decreases by 1. Okay, what about the particle that was what about the first particle that was that tried to went through the first barrier? That will remain as it is, but it going through that first barrier, it actually created another particle of k-1 kilogram, which is moving to the opposite direction. So if that particle is going to the right direction, then the created new particle, remember, created new particle was going to go to the left direction. What we exactly have to find out is how many different particles are being created. Now, it might happen that those different particles would have same mass. It doesn't matter, but I have to find out what are the different particles that are being created each time. Now, how far this thing can go? They have put out a statement that this would not go until k is 1. So decreasing this kilogram, if going on and decreasing until when k is equal to 1, it will stop doing what it was doing, which means decreasing by 1. So the operation is going to stop when k is equal to 1. So that's the stopping position of R. Now, k can be up to 1000, n can be up to 1002. And let's begin with the process of what about the second barrier. What if it passes the second barrier? What's going to happen? Okay, so what was the first action? The first particle went through the first barrier and with also k kilogram, but in doing so it created another particle, produced another particle of k minus 1 kilogram, which will go to the opposite direction. Okay, so this will be okay. So in this case, okay, I have right now I have two different particles that are being produced. One is that and one is that. And what about the particle that went through the first barrier? It's gonna have k kilogram, and once it gets past the second barrier, what's gonna happen is another particle is gonna create it, but in the different direction with k minus 1 here, k minus 1. It's gonna go to the different direction. Now look, now that's a very interesting part. What's gonna happen here? This will work, okay? This particle, which was going to the opposite direction, created from the second barrier by the first particle, which was going through forward, okay? It will always go forward and it will end its line just like here, the last barrier, you could say. It will go through. What about it created the new particle in the second barrier? What's going to happen now? Now, let's take a new color here to explain it more interestingly. Let's take a violet color. I guess it's gonna go well. Okay. Now, what about the particle that was created from the second barrier? What's gonna happen is, okay, he will go. Now for that particle, this is the first barrier, and he's gonna go past, but this particle's mass is k minus 1. Also, in doing so, he also created another particle, k minus 2. Absolutely, because I've said that once a particle gets past or gets through one barrier, it produces another particle in a different direction with the previous particle's weight minus 1 kilogram. Now, it will end if k is equal to 1. Now, I'm speaking in general purpose. If it's k minus minus, when it decreases, at some point it's going to be equal to 1, but I'm actually trying to explain you how far it will go, how far the length is. It will go. Now, look, k minus 2 created from here. Now, this k minus 2 is going to go past here, k minus 2. But in doing so, it also creates another particle, k minus 3, which is going to go to the opposite direction. Also, it's going to come here, and it's going to pass through this barrier, but in doing so, it's going to also create k minus 4 particle, which is going to go to the different direction. I hope you get that, what I'm trying to understand. So it actually does become a very complex situation. And just a circumstance where in between two barriers, look how many possible interactions or particles can begin with. I'm talking about different particles. How many? Just imagine. That's exactly they have denoted that it's going to be very large. The multiset is going to be very large, so you have to output it modulo 10 to the power 9 plus 7. Okay, so I'm actually reading those and analyzing all of this, you will come across a situation that, okay, this is getting very messy and complex. So then I actually try to find out, okay, let's make it simple and easy. What actually is happening? Now, in order to try and find out all of the cases, I actually focused on the recursive approach, which is just thinking about two situations. There can only be two situations here. What are those situations? Let's denote those situations here. Okay, let's take an eraser, I believe. Okay, let's erase everything and try to generalize everything. So instead of thinking so complexly, I came across a situation. Come on, don't be like that. It's lagging. Let's see. It is lagging. Oh boy. Oh boy. So, okay, let me explain you till it comes back to its position. So, I actually tried to find out just simple two observations. What are those observations? The observation is that, okay, it came back, I guess. Okay. Where's my freaking pencil? Okay. So, the two observation is, okay, particles can go from left to right, either from left to right and from right to left, okay? Right to left. So these two situations can occur. Now, when will I add, or when will I know that a new particle is about to begin its approach, or it's being produced? Only when it's being created at some barrier, from some barrier. Now, it's going to happen in two conditions. When one particle comes across from left to right, then I know that there will be produced a new particle which is going to be in the different direction of right to left. Similarly, if a particle comes from right to left and he goes through this barrier, then I know that I'm going to be adding one particle, because one particle is going to be created from here, which is going to be in the direction from left to right. That's it. Basically, these two situations help me to cope up with all of this mess of test case. Now the question comes, how big is going to be? It's going to be very huge if you do it brute forcefully. So what I did was, yes, I tried to memorize it. Now to memorize it, I know that I have to do DP. And for DP, to find out DP, I need to know how many states will I get. Okay, now how many states are there actually? Interestingly, this program or this memorization DP array, I found 3 states. What are those states and how did I find out those states? Now, first of all, I know that there are n different barriers which particles is going to pass through to it, and there you go. Okay, so I know that there are n different barriers, and I also know that yes, no matter what happens, particle is going to have to go through each and every barrier. So I get that this barrier, this is going to be my one state DP, because it's going to change every time. It's going to go either I plus 1 or maybe I minus 1 in some case. Okay, when new particles being produced, it's going to change its direction. Okay, so definitely this is going to be one state for sure, which is n, 1 to n. Okay, and what about the other state? Now the other state is going to be k for sure, because k is going to change. I know k is going to change because when a new particle is being created or it's being produced, its age or its weight is going to decrease by 1, and so definitely I have to consider my k. And another state is going to also be added, which is the two conditions that I talked about, from left to right. If particles come from left to right, for that I'm tracking out a flag value of 0, and if particles come from right to left, to indicate that the particle that I'm working with, it's coming from right to left. For that, I'm mentioning my FL or flag value as 1. So I have two values. These two values is going to be considered with another state. So of course these three types of values are going to be changed. So definitely they are going to be in my state, DP state. So I've got three states. One is for n, one is for the weight, and one is for the directions from where the particle is coming. So instead of for the new particles approaching, I'm just adding the answer value to find out how many different particles. Now also, after finding out everything, you will also have to add 1. Why is that add 1? Because initially they have said that you will have a particle by yourself. That particle is going to go. So for that particle also you have to add 1. That's for sure. Okay. Apart from that particle, everything is going to be calculated inside my solve function, which is going to be a DP function or recursive function, which I'm going to be memorizing with a DP approach. Now, if I tell you, let's take you to the code part now, so you can understand it more clearly. Okay, let's consider. Come on, the connection is lagging a bit. Okay, so this is the function here, and this is the function here. So let's talk about the main function here. Taking the test case, and this is the mem set of DP. I'm just initializing each and every value of the DP equal to 1. I know that n is going to be up to 1000. If n and k are up to 1000, I know that 2 times 10 to the power 6, it's between 1 second for sure. And also I've got test cases up to 100, but they have said that each and every test case, they have said here that sum of n over all the test cases will not exceed 1000. So I could consider it. If there is only one test case, there might be up to n equal to 1000. So one test case n could be up to 1000. So 1000 times, it's gonna be in between 1 second. So I'm pretty sure DP is gonna work. So the total complexity was, of course, n times k times 2. And now let's begin to explain what is happening here. Initializing DP with -1 for the memorization purpose, and this is the answer. Now this additional one, I've told you why this additional one, because the additional particle is going to be given to us, which we're going to be experimenting, start or commence experimenting. And for the next part, the rest of the part, we're going to be going for the solve function, starting from the first. Now I have here the indices are from 1 till n. Okay, one based index. Now 1 till n, it's going to go inside the solve function. First is the first barrier that we're going to go through. This is the k. We know the first particle's weight, which is k, and equal to 0, 0 meaning this particle is going from left to right. Now here, inside this solve function, the main game begins here. Also, I forgot to tell you what are the test cases is going to be, right? What could be the test cases? So here I have mentioned 3 test cases that could happen. One of them is when the ith particle crosses all the barriers, which is going to be if I is greater than n. This is the general test case. Also, if that ith particle gets past, if that ith particle is coming from right to left and it gets past my first barrier, then it's also going to be considered another base case. And apart from these 2 base cases, I have got another base case, which is if k becomes equal to 1, the operation stops right there. So these are the 3 main base cases. I hope you get that. And this is the memorization tool, and this is the fun part. Now FL equal 0 is considering that if the particle that we're working on, if it's coming from left to right, what is going to be our approach? Now I know if it's coming from left to right, I know that new particle is going to be produced, and it's going to be from right to left. So if it's going to be from right to left, I have declared it inside my value. There can be two other options for that particle. It's going to go of course it's going to go forward, but in doing so it's going to create another particle from right to left. That's why one is adding here and mentioning that that particle that was created or commenced from there, that's direction is changed from left to right to right to left. That's why this one is indicating. Similarly, the same thing, just in reverse order for any particle coming from right to left. I hope you get that here. And finally, this is mod. This mod is actually for if the result is going to be very big, we're going to have to consider inside our mod value, because the value is going to be so huge amount of values is going to be produced, or huge amount of particles is going to be produced. That's why we had we just had to do a mod and modular operation, and finding that value we just added with extra 1 for the initial purpose particle, and that's how we actually did this problem. I hope I made you understand that. So I hope you get the intuition behind everything else, and till next time, goodbye.